In this video, we'll look at electrophilic addition reactions of alkenes. So first, let's remember that we've already seen that alkenes can react as nucleophiles. That means that they react with electrophiles, or they attack the electrophile, to form a new carbon electrophile bond. Our simplest electrophile is an acid. And so an alkene can react with an acid like HCl to form a new carbon-hydrogen bond and a new carbon-chlorine bond. Alkenes can also react with other acids like HBr, H2SO4, H3O+, and so on. And remember that we draw a curved arrow from the nucleophile to the electrophile. So here from the alkene to the hydrogen or the proton of HCl. And then we draw another curved arrow to show that the hydrogen-chlorine bond breaks. And this doesn't immediately give us the product, but instead forms an intermediate, a carbocation intermediate. And from this intermediate, the chloride anion attacks the carbocation, and this leads to the formation of the new carbon-chlorine bond. Also remember that in this first step, when the alkene attacks the proton, we form the more stable carbocation intermediate, meaning that we could have placed the hydrogen on the left side carbon and the carbocation would end up on the right side carbon. But that carbocation would be less stable because it's only a primary carbocation, and the one that we formed instead is a tertiary carbocation. So again, remember that the more substituted carbocations are the more stable carbocations. That means that in this reaction, only one of the two isomeric products forms. The chlorine only ends up on the more substituted carbon, with the hydrogen on the less substituted carbon. We say that this reaction is regiospecific. And for these electrophilic addition reactions, this regiospecificity is called Markovnikov's rule. And Markovnikov's rule states exactly what we saw, that the X group will attach to the more substituted carbon, and the hydrogen will attach to the least substituted carbon. Now let's look at the energy diagram that corresponds to the reaction we just saw. These reactions are exergonic, meaning the products are lower in energy than the starting materials. And there is an intermediate and two steps, which means the energy diagram will show two transition states, one for each step. And in these reactions, the first transition state is higher than the second, meaning that it takes more energy for the alkene to attack the acid than it does for the chloride to attack the carbocation. Each step has its own activation energy associated with it, and the overall activation energy for the whole reaction, in this case, is the energy difference between the starting materials and the first transition state. Now remember that this intermediate is the carbocation. And we had two choices of carbocations that we could form. That means that there are two possible intermediates to include in our energy diagram. And the transition state for the less stable intermediate will be higher in energy than the transition state for the more stable intermediate. So here we're just looking at the first step of the reaction. And remember that a lower transition state energy means a lower activation energy and a faster reaction. So the reaction will proceed through the lower barrier pathway to the more stable carbocation. So once again, a lower transition state energy means a lower activation energy and a faster reaction. So the reaction will proceed through the lower barrier pathway, the one shown in black, to the more stable carbocation, the one drawn in blue. We'll end here by answering the question we posed at the beginning, to draw the reaction products and intermediates and map the flow of electrons with the appropriate curved arrows. I always like to start by identifying the nucleophile and the electrophile. The alkene is the nucleophile and the proton is the electrophile. And you might draw out the HBr to help you draw clearer arrows here. Then we draw an arrow from the nucleophile to the electrophile. This will form a new carbon-hydrogen bond, which means the HBr bond will break, and those electrons in that bond will go to bromine. This gives us the carbocation intermediate. And remember, we want to be sure to draw the more stable carbocation. Here, that's the secondary carbocation. Then the bromine attacks the carbocation to form the reaction product. And here the bromine, or the X group, will be on the more substituted carbon, consistent with the Markovnikov selectivity.